you so much for the kind introduction. So, and yeah, welcome everybody. I really appreciate that you all came here despite the super nice weather outside. So, yeah, I really appreciate this. And yeah, today I want to talk about how, let's say, we as a academic research community can build open language models for Euro. And this kind of represents kind of the lessons learned that I basically learned in the recent years while trying to build LLMs. But before that, I just want to make like a quick introduction of myself and especially highlight basically all the kind of stations that I went through until I arrived at the point of my career, which I'm now. And everything essentially started here, right, at TU. So I did my bachelor's and master's at TU. I studied Wirtschaftsinformatik, information systems and management. And I even also had lectures, I think, in this particular room. Back then, they didn't had nice chairs like this. So this changed at TU, right? Yeah. I studied here, and during my studies, I also did a research internship in Tokyo at the National Institute for Informatics. So there's a, I think, not very well-known program between TU and the NII. So in case you're interested in going to Tokyo, please reach out to me. And then after my master's, I did my PhD at the University Göttingen. Even though I never left Berlin for this, right? I was a kind of an external PhD student. I didn't want to move away from Berlin. So I had basically my PhD position at University Göttingen. But at the same time, I stayed in Berlin to work at the DFKI, where I was a researcher during my PhD and then also after the PhD. And just recently, I was a visiting researcher at Barcelona Supercomputer Center. And now, as you just said, essentially, basically starting from this month, I left DFKI to start working at Deutsche Telekom. But just to mention also two things that I did basically aside from my, let's say, kind of professional life. That is one that I co-founded the Open Legal Data Project, which you already mentioned, right? It's a project about open sourcing legal documents to the general public. And also, I co-founded the Oxyglot initiative, but I will come later to this again. So today, I want to start with a brief overview about kind of what are large language models to get basically everybody on the same page. And then I want to explain how you would build such a large language model and especially also highlight the challenges that I or we, with my fellow coworkers, faced while building language models, especially for the European context. And I want to end the talk with, let's say, more motivation for you in the sense that I want to show you how you can actually contribute to LLMs. But to get a rough understanding, I want to start with a question to you, to the audience. So who of you know what this logo represents? Okay, yeah, that's easy, right? Obviously, it's ChatGPT, right? It's the slides are already. This one is a bit older, so back then, not all the slides, not all the hands went up. But so you all know ChatGPT, but kind of. When was the last time you used ChatGPT? So who used ChatGPT in the last months? Okay, and who used ChatGPT today? Okay, so I see a lot of heavy users here. But of course, I mean, this talk should not be about ChatGPT, but rather about open models. So who knows this logo? Oh, okay, surprising many. Great. So for who doesn't know what this is the logo of Mistral. It's also a startup which publishes language models. So since you all, I guess, at least have experience with using language models, I try to keep kind of the kind of background rather quick. So let me just briefly go through the basics, right? So what is a language? So a language model in its sense is just a distribution, a probability distribution over sequences of words. So given words, like the historical words, you want to predict the next word. And you train a model, so you adjust the parameters to optimize basically this prediction. And this means that essentially for a given input, like the dog runs, the language model predicts the probability over its kind of vocabulary, what would be the kind of next most likely token. And if you want to use something like this, you do this in an autoregressive fashion. So you go and predict token by token. So you repeat the prediction again and again. So you have your, in this example, the initial prompt, and then you just keep predicting the next token until you reach a kind of special token, which is here the stop token, and the stop predicting. But this is just like a quick example to get everybody on the same page. So just predicting the next token seems at first super simple, but kind of the big shift in the NLP research was that when people starting to realize that even though this is a relatively simple task, it is kind of universal. So most of the tasks can be kind of formulated as a next token prediction task. So you can make a question answering, you can make a translation or a summarization, even math can be formulated as a next token prediction task. And this was kind of a big shift in the sense that prior to this, in the research community, you tend to produce more specialized models, one for each separate task. And now with this kind of universal objective of predicting the next token, you have or end up with a more general purpose model that can generalize across different tasks. This was just generally like how a language model works, or what the sense is. But today we are mostly talking about LLMs, so large language models. And for this, just a quick recap. So language models are kind of a subset of deep learning and machine learning. So they learn or are trained based on data, right? You feed data into the model, you adjust its parameters to optimize its objective. So it's a statistical method, right? So given one variable X, you want to predict another variable Y. And then based on some methods, mostly gradient descent, you optimize this prediction. And this is something you always, I would say, should keep in mind, because like with the whole kind of discussion now about AI, it's always important to remember, okay, it's statistics like in its core, like not saying that it's less valuable, but it's kind of you always should remember the kind of the basics. But we are talking about language models, right? So in this case, X and Y, so the variables, they are natural language text, right? And the question here is, okay, how can we actually get from text to something that we can do computations with? And this is kind of the very first step of the language model. And this is the tokenization. So tokenization means that you take an input text and you segment the text into tokens. So for example, here we have one German example sentence. Der Hund läuft über die Wiese. And in a very simple example, when you just segment this text by weight spaces or special characters, you wouldn't end up with the kind of words as tokens. And then you have a mapping from a token to a token ID. So you have a fixed and limited vocabulary, and map kind of these to vectors, to numerical vectors. And based on these vectors, you then can do the computations within a language model. And the example that I used here is really just an example. So in practice, you don't do this separation by white spaces, but you learn kind of how to segment the text. and it's usually done on a kind of subword level. And how the GPT tokenizer is tokenizing a text is also shown there. And when you then train a language model, you kind of optimize the values that you get for the token vectors. But yeah, this shouldn't be kind of the kind of main point here. Just for you to understand kind of the basics, because tokenization is really language specific, and I will kind of come back to this later. Apart from this, kind of after you kind of tokenize the text, you feed the data into typically a transformer model. I don't want to go into the details here. So the only thing that I want to kind of highlight here is that kind of through the transformer architecture, or the model architecture, it was possible to make the models really large, right? So in my opinion, kind of the main contribution of the transformer is that you can run computations in a language model setting much more efficiently and also scale the computation. So language models are not really new, right? So there were language models already in the 1950s. But just recently, through the transformer, we made a shift from, let's say, language models to large language models. And this is really where the kind of scalability comes in, that the transformer architecture enables. And I mentioned already, okay, the models are getting large. But here, the main takeaway should be that the models are getting large because people started to realize that if you make the models larger, and here larger means in terms of the model parameters, in terms of the data that you train a model on, but also generally in terms of compute that is used for training a model, that as soon as you make the models larger, the models get better. So you actually can predict how good a model gets depending on how large you make the model. And this was kind of a big kind of discovery, because then you have essentially one clear path you need to take in order to improve your model, essentially scaling it up. And by scaling up, what was also discovered was that you essentially unlock new capabilities in the model. And here on the slide, you see two examples. That is one from a language model about the mathematical capabilities. And you see here in the slide that at first the model performs kind of on a random level. But after a point, it reaches a capability or unlocks a new capability, and you see essentially above random performance. And this can be seen across many other different tasks, also here for translation. So let me just quickly summarize kind of what large language models are. So large language models are statistical models that learn a probability distribution over a sequence of words. And they are trained to predict the next token. So when they are used, given an input text, they predict the most likely token, or the token with the highest probability. And in order to compute based on natural language text, you always first do this tokenization step, which converts the natural language text into numerical vectors. And as I mentioned, kind of transformer architecture kind of was the first architecture that actually allowed scaling of these models and made them actually really large. And because we now have very large models, these large models enable generalization and also solving new tasks, but at the same time, they require large resources, so in terms of data and compute. Okay, so this should be kind of the first kind of recap. So I hope we are now, at least everybody, a little bit on the same page. And now I want to start with the kind of work that I've been doing. So I want to explain you basically how you would build such a large language model in practice. And this in the open for Europe and as an academic researcher. So what do I mean by this? So first, what are open LLMs? So you all used apparently ChatGPT. ChatGPT, even though it's kind of free to use, is not something I would call open. Open is more like in the sense of open source, so something that you can inspect, something that you can use on your own infrastructure, and not like a service like OpenAI where you just have an interface, an API, and where you essentially need to pay for using the model. But so what does this mean? So here I just use the definition, the open definition, and that is that it's not just that open source means that you just can see or inspect the source code. It also comes with all sorts of different associations, especially regarding the free distribution, and also that you can build derivative work. So it means that you can take like an open source project and adjust this on your own needs and then also republish it. But the reality is, kind of in today's LLMs landscape, is that, of course, you have all the kind of commercial models, which are not open at all. But then even you have models which claim to be open, but they're not kind of truly open. You rather have something like open weights. So for those who use other models, there are, for example, the well-known Llama model and other models, for example, the one from Cohere. They are open in the sense that you can download the model weights and run them locally on your machine. You can run them on your own infrastructure, but they are not open in the sense of kind of the open definition of open source, because there are other license restrictions. Like, for example, you might not use such a model for a commercial purpose. You might not redistribute the model under specific terms of licenses. So when I say I want to get something that is truly open, I not only want to have open weights, I want to have a truly open source license. So this means something like Apache 2 or MIT license. So where you're really free to use essentially the model for whatever purposes without any restrictions on your own. But at the same time, when we talk about open source, also more from a kind of software development perspective, open source means that you want to expect the source code, right? And as said, a language model is a statistical model. So it is essentially defined by the data that the model is trained on. So in this sense, when I say, okay, we want to achieve open models, this also means that we want to make the training data open so you can actually see what the model was trained on. And if you look into the kind of LLM landscape, what models are available, even, for example, the Mistral model that apparently many people used already, there it's not known what the model was trained on. So this would fall also under the category of the open weights, but not under the definition of, okay, that you really have an open source model that you know what the model is trained on. So there are a few exceptions, and this is kind of what we, or I and my work, aim for, that we really have truly open models. Then the second goal that we have was that we want to build models for Europe. What does it mean? So Europe as a continent, we have many different languages. So you know, ChatGPT, you probably use it on English, but there are many other, especially low resource languages, which are not supported by the big models. And this is kind of where our work aims to, that we want to make the models also accessible in a more low resource setting for lower resource languages. And this does not simply involve making a model speak in a certain language, but it also incorporates that we want to kind of establish cultural knowledge in a model, right? So even though, let's say, ChatGPT probably can answer a question in German, it is still heavily influenced by kind of the English web and especially the US centric web. So you can see this more as a, let's say, like ChatGPT, let's say as an American who speaks German, right? But it's not kind of a German with the local cultural background. And this is kind of what we aim for with our work. Okay, but what does it mean in practice? So when you think about how to use a language model in a different language, the first point you approach is, as I said, kind of the tokenization. And this is really language specific. So I already showed kind of this one example of the GPT-4 tokenizer, which is primarily optimized for the English language. And this is kind of easily seen in this example, where you have one word, zusammenarbeiten, which you then take and feed through the GPT tokenizer, is tokenized in 5 different tokens. And if you then use a German tokenizer that we especially kind of trained to be well suited for the German language, you only get 2 tokens. And this at first doesn't sound too bad, but the thing is that kind of the way how a text is tokenized affects everything that comes after the tokenization, especially the costs. So right now, when you want to use, let's say from a company, if you want to use the OpenAI API, you pay essentially per token. And this is because kind of the model basically computes on a token level. So you also have more costs in terms of compute when you want to run a model on your own infrastructure. This essentially goes back to the architecture, the transformer architecture. And this has a quadratic complexity with respect to the tokens. So this means that kind of the number of tokens you feed into the model is really crucial how kind of compute intensive the transformer is. And this is one result that we did in a study in the OpenGPTX project with some colleagues from Fraunhofer and TU Dresden, where we looked into how different tokenizers trained on different languages affect not only the costs, but also the actual model performance. And what we observed was that if you talk about the costs, that if you take a suboptimal tokenizer, you end up with up to 68% higher training costs, which is quite significant when you think about on kind of how much data or how much compute goes into the model training of a large language model. But it's not just the training costs, it's also the actual model performance, in a sense how good a model is on particular tasks. And this is something you can see here on in the table, where you can see the difference between kind of the worst tokenizer and the best tokenizers. And this is quite significant for all different tasks. So the tokenizer is one thing, but the main part, let's say, of a language model, as I said, right, is a statistical model, learns from the data. And this is also something we worked on, but I would say, pretty much underestimated kind of at first. So when I started working on LLMs, I was kind of naive to think, okay, if you want to train a language model on text, you just take text from the internet, and there's plenty of text, and this should be sufficient. But it turns out that's not the case, right? And that data matters a lot. So, and this is by now also, I would say, pretty much understand throughout the community, and also, of course, throughout the kind of the big tech. Just say this here and there, that modeling is one part, but what really defines if a model is good or bad is essentially the data quality. So what the model is trained on. And this is the biggest differentiator between the models, how good they are or not. And the other thing is, of course, that models, let's say in the research, there's a lot of activity regarding model architecture, how you train a model, how you design a model. But what essentially stays is the data, right? So that's kind of a big part of how a model kind of differentiates. But what does it mean to have a training data for a language model? So typically today you have 3 stages of training. So at first you do unsupervised pre-training. This means that you train a model really on this next token prediction task, simply on plain text. So, and this is basically where a lot of kind of the big big amounts of text come into play. And just to give you an estimate, so for many models, this is kind of secret, you don't know. But let's say Llama 3 just recently announced or published that they trained this Llama 3 model on 15 trillion tokens. Yeah, and this is an insanely big amount of text. This is roughly equivalent to 500,000 years of human typing. So that's a huge database of text, which of course is also not really feasible to manually inspect, right? It's just simply too much text. And this text is usually sourced from the web, where Common Crawl, like a nonprofit, is providing most of the data, but also other sources like scientific literature, news, web forums are used for this unsupervised pre-training. In the next phase, second stage, you do supervised fine-tuning. So this is more task-oriented. So I mentioned that language model essentially predicts the next token. So this means that, for example, when you would use a question as a prompt, let's say classical unfine-tuned language model, which was just pre-trained to predict the next token, might not give you an answer to your question, but simply would respond with another question. Because if it was trained on web text, there are plenty of websites which just simply list questions. So it could be that next kind of most likely text on a question is just another question. And this is where this fine-tuning comes into play, that you have specifically designed input and output pairs. For example, a question and an answer, a text and a summary. And this is basically where you make the language model work on specific tasks. And then as a third step, you have the alignment phase or the preference tuning. And this is more, I would say, kind of a recent trend that you see, that you simply not want to have an answer, let's say, to a question, but you want to have an answer that satisfies essentially the user needs. So it's easily readable, it's easy to understand, it actually explains also what the answer to the question is. And this is where this preference tuning comes into play. And this really involves that you have labels of like the good answer and the bad answer, or rankings of kind of the answer quality. And if you want to kind of build such a training data set, you essentially start with a large amount that is relatively cheap to collect. And as soon as you go through the stages, the scale of the data gets smaller, but also the costs in acquiring such a data get higher. But what data do we have essentially for Europe? So this is one chart that we collected for a project where we wanted to train a European language model. And this is the data distribution by language in one of our data sources, which is called Oscar. And what you see here is that even though this data collected from the internet, it's heavily dominated by English. So English accounts for roughly 40% of the data. And this is a big challenge. So as I said, kind of our goal is not to train a language model on English, on a high resource language, but also on other European languages like Hungarian or Croatian, where you see, okay, there's almost, or let's say below 1% data available in the data sources that we can easily access. But what can we do kind of to get data, or where's the data in the end coming from? Well, I already mentioned that the language model providers, they don't really say where the data is coming from. So this is what I mentioned was, okay, they are not truly open source because you don't know what the model was trained on. So also an example from Llama 3. So they say, okay, it was trained on 15 trillion tokens, but they're not really precise. They simply say, okay, Llama 3 was trained on data from publicly available sources, right? That's really the statement they give. So it's like, okay, it's nothing at all, right? You don't know what this data actually, or where this data is coming from. But what we do know is that most of the data comes from the web, because the web is the only source that is easily accessible, provides large amounts of data at a very low costs. And one major source for web crawl data is Common Crawl. That's a US-based nonprofit that crawls the web and provides basically these crawls as a download for free. So this project at first was more as a kind of alternative kind of for search engines. So search engines didn't need to kind of build their own kind of crawling. And then it was also used for archiving. But just recently, Common Crawl got just much more attention through the language models, because it provides a really large scale data sets. So this is really in the petabytes of data that they provide. But the problem here is that, well, okay, it's a US-based nonprofit that is doing this. And they're doing this as a crawler that operates from the US. So it has a US IP address and also a US user agent. This means that when it accesses a website, the crawler appears to the website as somebody from the US. And you probably know that a lot of websites, they do some kind of localization. So depending on where the visitor is coming from, they adjust the content and they present the content in the language the user expects. So that's why we also see much more English content in web crawls like Common Crawl, because they are operated kind of as a US crawler. But one thing I would like to mention here is that there are initiatives like the Open Web Search project that especially try to provide an alternative from a European perspective. So they do crawls from a European IP with a European user agent, so with European languages, and specifically also designed to cover European websites. So web crawls are kind of the main source, but of course there are other sources like smaller data sets, which are probably in a more like high quality, but at the same time also in a smaller quantity. And this can be scientific literature, news, or web forums. And the kind of work that we did here is especially about these data sets. So there are many different data sets, but if you want to train a language model, it's a lot of effort to do the pre-processing, to source the data, to find the data, and also to check whether the data is published under a license that you basically agree upon. And this is a work called LM Datasets. It's an open source project. We also have a publication on this where we actually provide a lot of different data sets for more than 32 European languages with approximately 2 trillion tokens. So this is comparable to Llama 2, not the Llama 3, but we are working on extending this to also increase the dataset size. This is, as I said, open source, can be used and is also already used by some projects to train large language models. But what about the open aspect of European LLM data? So I already mentioned that the commercial providers like OpenAI, they keep this kind of as a secret, what the data was used for training. One, of course, it's kind of their company IP, because it's kind of defines how well a model is. But there are also many legal reasons why they don't share what the model was trained on. So there are a lot of regulations, like privacy, right? You don't want to include personal informations in the model and training data. But also at the same time, you have copyright reasons. So they are publishers, they have licenses on their data. And of course, they don't want to have somebody else profiting essentially from their own data. And because the laws are different, especially if you compare the US to the EU, this is also quite challenging, let's say from a perspective, from a European perspective, because in the US, for example, one thing many providers also, for example, Common Crawl, are kind of, let's say, arguing that what they do is fair use. So they don't basically copy all content from a website, but only a subsample the website. And this is basically a fair use term in the kind of legal system in the US. But this term does not exist in EU. So in the EU. So this is something we cannot make use of. And this makes it, let's say, also legally a bit tricky, kind of what data we can use because there's so much uncertainty. So essentially, this is right now more of a legal gray zone. And of course, I'm not a lawyer, so I can't give any legal advice here. But the big challenge is, and also from my experience when you talk to lawyers, is that there's no answer to this yet. So because the whole topic of LLMs or generally generative AI is still pretty new, our legal system did not kind of adjust to this technological progress. So right now, if you talk to lawyers, they cannot give you a definite answer, kind of what data it's okay to use and what not. But there are currently ongoing lawsuits, for example, one between OpenAI and the New York Times, where it's explicitly about whether OpenAI used New York Times content for training models like ChatGPT. And I hope that in the future this will get more clear. In Germany, there are also currently some law cases going on. So right now it's more of a gray zone, but this will likely change pretty soon. But one thing here as a kind of academic researcher is that as long as you do science, as long as you do language models for a scientific purpose, there are exceptions. So in Germany, there's something called Schrankenregelung, which means that as long as kind of the main purpose is science, you're accepted of some copyright restrictions. So this is something kind of we also benefit from, but at the same time, it's also a challenge because if we want to make models available, right? We not only want to make this available for science, as I said, we don't want to impose license restrictions. We want to make them also commercially available. So this is also a challenge you need to basically balance. So I already mentioned the tokenizer. I mentioned the data. And then we have kind of as a third ingredient, the compute resources. And this is something where we as Europe really lag behind. So just to give you an estimate, right? So Mark Zuckerberg recently announced that Meta would have, I think by the end of the year, something around 350,000 H100 GPUs. So this is kind of the most recent NVIDIA GPU series. In comparison to this, the Supercomputer Center in Barcelona, where I was a visiting researcher, has one of the top kind of supercomputers in Europe, and they don't even have 5,000 GPUs. So a single US company has a magnitude more resources than kind of the entire European research community. And this is also reflected in some kind of settings. So when you want to use public available compute infrastructure, for example, you get a compute budget that you need to spend on a monthly basis, which is not really usable if you want to train a large language model, right? So usually, like in such an experiment, you would do at first very small experiments. So you would have kind of a low kind of need for compute resources. And then in the end, you would do your big model training, and then maybe in the end, some smaller evaluations. And this is currently not really kind of covered by the current system, how you as a researcher can access compute resources. But already mentioned that I'm coming from an academic background. So we are trying to do this as a kind of academic research project. And there are some other general restrictions and challenges that come with this. And this is primarily that kind of if you want to build something like OpenAI did with ChatGPT, you're essentially competing with a company that built a product. So ChatGPT, even though it's kind of the primary example for LLMs, it's not just an LLM, it's rather a product. So a lot of different tools and filters built around an LLM. And the thing is, if you do academic research, that's not your goal, right? You are not meant to build products. You're meant to build prototypes and to do research. This is not really in the scope of a typical research project. The other thing is that just like how research is typically organized is that the research is essentially done by PhD students who publish papers, right, to get the degree. But the problem is if you do an LLM project, this is not really aligned to the kind of PhD publishing system, because you have just like one big thing, and it's very difficult for PhD students to do basically a PhD on LLMs if they just have like one big thing and not many small papers that can be combined to one PhD thesis. But there's hope. So other sciences, especially physics, they already have something like this. So in physics, you probably all know CERN, right? This is also about one big project. They build one big machine where a lot of students work on and they get their PhD. So there's already the tendency, or let's say a discussion going on about that we can build something like CERN, but for AI research. But I don't want to be pessimistic, right? So there's still plenty of research that you can do. And I just want to give one example about kind of a research that we did at DFKI. So I mentioned, okay, making large-scale experiments, that's a big challenge. But you can, of course, pick smaller niche topics, work on a sub-problem. And this is what we did here. This was a research on transfer learning, where essentially the idea is that you make use of existing resources or existing, for example, trained language models, and then adapt them instead of training a new model from scratch. And this is what we also did here, especially for the context of cross-lingual transfer learning. So we took, let's say, an English model, transferred it to German. And this worked pretty well. So here we achieved a reduction in training costs of up to 80%. But this is just one example. The main thing I want to promote here is that even though it's kind of tricky to kind of compete in the LLM landscape, is that we can do something as a community. And this is where the kind of community-driven LLM development comes into play. And this is about Oxyglot. Oxyglot, I mentioned this already in my introduction. That's not an actual research project. It's more of an initiative. It's about a research collective, so a loose group of people who are jointly working on the topic of LLMs. And we already released models which are freely available on an Apache 2 license for European languages. And this is an ongoing project. So given the time, I think I just skip the details here and just move to the part where I say, okay, it's an open community. So if you are interested in working on language models, I pretty much invite you to join our Discord server, where we kind of work as a community on LLMs. And depending on kind of your skill background, there are all sorts of different things that you can actually do to help supporting European LLMs. So what can you actually do? And here I just want to give a few examples what you can do for language model development. So the first one is simple in the sense that it does not require any sort of like technical knowledge. So I mentioned that most of the data that we are training language models on is coming from the web. And this is a big challenge to actually find out what data is actually the good data, what is the data I want to train a model on. And here we are working on kind of curating web data in the sense of collecting information about, okay, what is a good website where you want to train a model on. And here in the table, I just have one example about kind of the top domains from our German data from one subset. And the thing is, you might already see, so there are like some academic websites, Wikipedia, some official government websites, but there are also a lot of what I would call like dodgy website, like a climate conspiracy website, and also like Pi News, which is also kind of a more like right-wing conspiracy website. So this is something you probably, if you have somewhat kind of web understanding, can easily detect, right? But if you want to do this kind of on a large scale and with automated means, this is pretty difficult because the text look good, right? They have good grammar, they have a lot of content, so they are used for language model pre-training. But of course, this is the content you don't want to train a model on. So if you have some time, if you want to contribute something like this, please feel to check out the Git repository, where we kind of collecting list of good domains and bad domains where we want to train the models on. The other thing is, of course, to help with the construction of more supervised data. So supervised data, this is really about the kind of input and output pairs you train in the end or fine-tune a language model on. And this is more technical. So if you have some technical experience, for example, with web scraping, you can go and scrape websites, for example, FQAs from websites, so build a question answering data set. Another thing I would like to mention here is that if you want to move forward and actually kind of make models, there's one kind of recent trend, which is called model merging. I guess it's not very well known here. I was also pretty surprised when I first read about this like some time ago. And this is really about taking two models, to the weights of two models and merging them, kind of interpolating, aggregating the weights without no additional training. So this does not require big GPU clusters. This can be done most likely on your local laptop. And what I'm showing here is just one example I did, essentially kind of on a, let's say, weekend hack, was taking two models, merging them, and in the end getting a model. Let's say I merged a German and an English model, and in the end getting a model which was better than the kind of single ones. So this is kind of a new trend, which I definitely recommend to check out, and it does not require any big like technical setup. At the same time, of course, there are like fine tunings. So if you're more interested in actually also training models, you can also approach us. We have some compute resources available for this. So if, for example, if you want to train a model for one specific purpose, this is possible with, let's say, the resources that we can provide, but also with free resources that you can find on the web, for example, on Google Colab. But the most important thing about building models is the evaluation of the models, because in the end, you want to know if the model is good or bad and kind of what path you want to kind of develop your model. And this is pretty tricky because the models are already, let's say, that good that it's very difficult to distinguish between, let's say, a good and a bad model. And especially because we're dealing with generated text. So there's often no clear right and wrong if you have a generation task. So this is not like classical machine learning where you have a classification where it's easy to say, okay, this is right and wrong. Generation is generally much more difficult to evaluate. So if you're interested in this, also please feel free to approach us. And the most important thing is here also to actually go and use the model. This is what often is referred to the wipe checking. So essentially just chatting with the model, trying it out, trying it on your own purpose. And this is something what we also observed from the community is super useful for us if we want to train models to get the feedback, what is working well, what is working bad, so we can adjust our training. And with this, I want to invite you to try out the models. So you can go to opengptx.dfki.de/chat and try out the Oxycloud models that we trained and test them. It's for free. It's probably not as good as ChatGPT, but well, let's say for some German tasks, it might be better. So, and with this, I would like to end the talk. So thank you so much for your attention, and I'm happy to answer your questions.
Okay, yeah, let's have a very, very quick round of questions, maybe 10 or 15 minutes. I will, or someone will pass you the mic.
Malte, thank you very much. My question regards these stages of training data you mentioned, which is very cheap in stage 1 and then gets more expensive because more human labor is involved. So actually it's 2 questions. The first question is like, how much data in this first stage, like unsupervised data, do you think we have already used or found? Like you mentioned these 2 trillion tokens you found of 15 trillion tokens for Llama 3. Is this like 1% of all human written text, or is it like almost everything? And the second question is, where do you think which data from which stage should one focus on to produce a better next model?
So regarding the first question, there was actually research published about this saying that we are running out of data to train these models. But I'm honestly a bit skeptical about this because I still think we are just scratching the surface. So the current main data source is Common Crawl. But as I said, also kind of for legal reasons, this is only a tiny subsample of the web. And there's many, many more different kind of data sources on the web you could use for training a model. So I think the rough estimate for kind of all Common Crawl is something around like 30 trillion tokens. So again, like double the time, double the amount of data that Llama 3 was trained on. But as I said, Common Crawl is only one source. And what essentially is already kind of well known is that especially like the big tech companies are now just starting to crawl the web themselves. So that's why I think now for example, it was now like the rumor that OpenAI might release a web search engine, right? Which comes also from basically the problem that they already solve a lot of, let's say, things that you need for a search engine. So they already do crawl the web themselves, like Google. They already do filter the web for high quality content, for training the models on. And then essentially kind of the search interface is probably also easily done. So that's why I think there's this rumor at least. But also apart from the web, I mean, there are many, many different data sources, libraries, which are kind of offline, which are not easily accessible. And now I think we would see many more data sources also become available because it's now more and more interesting also to use these data sources. And at the same time, what you also see is now that you would have kind of classical publishers also essentially kind of selling the data for LLMs. And regarding the second question, can you repeat it? At this stage, where to put the data? Yeah. So the second question was about kind of in what stage you want to kind of invest, right, your efforts. That's hard to say. So let's say it depends on your skill set, right? If you have capabilities of kind of filtering large data sets at scale, probably the first stage is the best one. But at the same time, also, this is also what we saw in our experiments, is if you build like small scale but high quality supervised data sets, this makes a huge difference. Like generally, like all stages are important. I wouldn't kind of differentiate between them.
Thanks, Malte. One question is about data mixing. So you collected the data and you're gonna conduct these 3 stages of fine-tuning and training. And for each stage, how do you think about the order in which you feed the data to the model?
Let's say the stages that I showed, this is also maybe to some extent with simplification. So what you also nowadays do, or what we are also experimenting is that you already mix kind of supervised data into the kind of pre-training phase, for example. So this is something what I think there's no clear consensus yet of how to do it. So this is something which we are exploring. And also regarding the order which you trained on, it's also, I would say, still an open research question, like how to do this in the most efficient way. There are indications that it makes sense to start, let's say, with the easiest data, very easy text that you can basically just simply learn relatively like language understanding. And then later on, as soon as you already kind of, you or the model acquired already kind of this language understanding, you start adding training data which is more complex, kind of requires reasoning, mathematical challenges, or more task-specific data. And languages, that's a good question. We so far did not consider kind of changing the order of languages. So my kind of, or let's say our current approach is to essentially try to sample from our kind of data set across all languages. But at the same time, and this is now kind of where kind of this mixing into the fine-tuning data comes into play, is that we not only have like different languages that we train on, but we also include translation data, during the kind of pre-training, because our assumption is that we do not want the model to learn languages separately, like in, let's say, separate islands you can think of, but rather already learn how to link languages together to have really this cross-lingual kind of transfer learning going on.
What's your stand on completely unrestricted models, basically, which can tell you how to build a bomb or stuff like that? And are your models completely unrestricted?
So when you say restricted or unrestricted, right, you're referring more to this kind of fine-tuning and preference training, which, just maybe to give some background, is, I would say, something that if you provide an interface or model like a chatbot, you should consider. But if you build something like a kind of foundational technology, which I would say was kind of my purpose, like for now, then this doesn't matter too much. So in the past, there were also some approaches, for example, where you used kind of keyword filters to filter basically web content. For example, to filter out adult content, you had like a keyword list, which actually led to the problem then, I think, in the, what was it, like GPT-2 model or something like this. In its vocabulary, it didn't have the word sex. Like, because it was like completely erased from its knowledge or from its training data. But my kind of my position on this is that you should not erase everything completely, because if you want to know, let's say, that something's bad, you still need to know about it, right? Because of this, we, for example, don't use this kind of word filters for filtering our language. And maybe another thought on this. In the end, technology, I mean, it's a tool, right? Can make information more accessible. Like with Google, right? You can Google how to build a bomb. So this is nothing which is completely new, I would say. In the sense, I think people who really want to find out stuff like this can always do this, can jailbreak the models, can find their way around it.
Hi, thanks for your presentation. I have a more organizational question. If you could share the slides with us somehow.
Yeah, sure.
So just maybe in Discord, we join.
Sure. Oh, I don't know if there's like a mailing list or something like this. For sure, we can find out a way how to share the slides.
Do you see any hope for there being a common incentive to provide the resources to train all these models to, like, even remotely compete with the big models, especially since they unlock new capabilities and or like, for example, a EU-driven effort, something like this, which would be really nice.
So yeah, maybe the picture that I painted was a bit pessimistic, I must admit. But I'm generally optimistic, and I think there are for sure reasons to believe that there's hope, in the sense that you will always have kind of like the commercial frontier models where you have kind of a performance gap. So some capabilities which they can do and, let's say, open models can't. But, and I have actually a slide on this, is what you can see is if you look in the kind of recent years, how the quality of closed and open models kind of changed is, and I hope this is somewhat visible, is kind of on the top you have the closed models, and on the bottom you have the open models, and you can see kind of both lines are kind of roughly approaching each other, right? It's not completely parallel; they are slightly going towards one target, so the lines would eventually meet at one point. So, in this regards, I'm pretty confident that. And this is something you can already see is something like ChatGPT. You already have now open source models which are kind of on the same level. And since all this is, it's not black magic, right? I think so sooner or later, you can also, as kind of Europe, can build something like this. So this is for sure possible. Not sure when, right? Things are moving slow, but they're moving in the right direction. So I mentioned, for example, this like CERN for AI, which I think would be a great initiative, because what you can see, especially like in the AI landscape, is that kind of scale is what you need, and you also need a kind of centralization, which goes a bit away from kind of a core European principle that you don't want to have everything centralized in Europe, right? You have also in Germany, I mean, you have many different AI centers, right? Which I get makes sense. Like you want to have something everywhere, but at the same time, this limits also kind of these effects of having all the people working on one problem in one place. That makes things difficult. And this is something what you have in the US, right? You have like Silicon Valley, where most people are, and that's where you have all the synergies. But this is, I would say, also if you follow kind of what politicians say, already to some extent understood. But of course, it's difficult to implement. So, but I mean, CERN is, I think, like the perfect example, right? So we just need to be, as a computer scientist, we just need to be more like what they do in the physics.